Last time we stopped here, we basically set up the power flow problem. So can somebody sort of summarize what we did? So I look back at this example. Can somebody tell me a summary of what we did? Sure. Exactly. So at a PQ bus, what are the unknowns? And V and delta. V and the angle are unknown at a PQ bus. At a PV bus, Q and the angle, right? And at the slack bus, I know V and delta, which means I can calculate my P and Q, so nothing is unknown at the slack bus. So we identified the variables and identified the buses, and we were able to construct our admittance matrix. So what is the order of the admittance matrix? What is the size of the admittance matrix? Hmm? Exactly. So the admittance matrix is the same size. It's a square matrix, symmetric, and it's the same size as the number of nodes that you have in the system, right? So that's what we did last time. And then today we will, so this is, and of course to fill up the admittance matrix, we said to fill up the admittance matrix, we need all the data of the various components. So the line data, the transformer data, all of that we had to plug into the admittance matrix, right? So this is how we set up the problem, showed, constructed the admittance matrix, but we don't know how to solve the power flow problem yet, right? We sort of have an idea of what we need to do, but we didn't do that yet. So let's see what we will do. So there are several methods that are discussed in the textbook. We will not discuss the Gauss-Seidel method. We will only do the Newton-Raphson method. So this is just a few slides in the Gauss-Seidel method. They're just two different numerical methods. Okay? So I just choose to do one so that we can move to a different topic and then this is the one that's actually used in Power World Simulator. So that's why we go over that. So what the Newton-Raphson method for power flow solution does is it sort of creates a computerized way of solving this power flow problem based on the unknowns and the knowns that you have in your system. So we construct, or we sort of put all the equations that we have in the format of y equals f of x, and y in this case is all the powers and active and reactive powers at the various buses that you are looking for, right? And then the v's and the deltas are also the corresponding angles and voltages at the buses that you're looking for, right? So we said if we have a PQ bus, I don't know V and delta, right? So there would be a delta corresponding to the P that I will calculate at that specific bus, right? So remember, at a PQ bus, I will have, P and Q known values, right? But I don't know V and delta. So I will need to find out the V and the delta. And I can find out the V and the delta by using the P and Q values that are given, right? So at the PQ bus, I can use two equations at that specific bus. I can use both power flow equations at the specific bus. Remember, these power flow equations are at every single bus, right? At every bus, I can implement the power flow equations. That means if I have a 10 bus system, I have 20 unknowns, right? And I have 20 equations, theoretically speaking. That's how I can start. Because I have real power equation and I reactive power equation at every bus. So we'll go through an example to construct this, but actually let's go through an example to construct this instead of so canvas, white background. So given a small system like this, so this is bus 1, bus 2, bus 3, and bus 4 here. Bus 2 is going to be my slack bus. Does not have to be bus 1. So I'll call bus 2 my slack bus. So I'll have my generator here at bus 2. And then I will have a load here, a load here, and a generator here. And I will have a line between these two here. Okay, so this is the system that I have. So again, the first step is identify your types of buses, right? So bus 1 would be what? Huh? It's a load bus or a PQ bus. Bus 2 is a slack bus. Bus 3 is a generator or PV bus, and bus 4 is another load bus, right? So these are the types of buses identified. The next thing we do is identify our unknowns. Okay, so the next thing we do is let's identify the unknowns, and remember the unknowns will be the v's and the deltas. Okay, because if I know the v's and the deltas, I can calculate the p's and the q's, right? So my unknowns, let's go by sequence through the buses, right? So at bus 1, it's a PQ bus. So what are the variables that I need to find at that bus? Theta, or yeah, the angle and the voltage, right? Because I have the real and reactive power, so I still don't know the angle and the voltage. So I don't know V1, and I don't know theta 1. How about at bus 2?
You don't know the theta.
No, bus 2 is my slack bus. So slack bus, we said we will know V and delta. So if I know voltage and angle, that's it, I'm done, right? And then bus 3, I don't know Q, I don't know reactive power. The reactive power is unknown. Voltage is known, so what I don't know is theta 3, angle at bus 3. And remember, I'm only putting angle here because it's always with respect to the slack bus. So I'm not putting angle difference, but regardless, let's talk about that. We'll construct this and we'll see what I mean. How about bus 4?
The same as bus 1.
Same as bus 1, so I don't know V4 and theta 4. Right? So I have 5 unknowns that I need. So I need at least 5 equations to be able to calculate 5 unknowns, right? Correct? I need 5. I have 5 unknowns. I need 5 equations. So what are the equations that I can use? What are the equations that I have? I know the equations would be the left hand, the left hand side of. Sorry, the equation would be the power flow equation that I can use, and it is something. So if I know, for example, P and Q at this bus, right, it means I can use the power flow equation for real power, the power flow equation for reactive power at this bus, right? So I can use P, the power flow equation here, P at bus 1, and I can use Q at bus 1. How about at bus 2? I know everything, so I don't need equations there. How about bus 3?
You use the voltage.
Hmm?
You can use the voltage to find the angle.
I don't know what. Yeah, but what equation can I use?
You can find.
Remember, I have P.
Okay.
So since I have P, remember our equation is P as a function of V and theta is equal to some summation blah blah blah, right? It was equal to this some big equation, right? That has V and delta or V and theta in it, right? So since I know P, I can use that equation, right? I can use this equation for real power. So I have 2 equations I can use every bus. The real power equation and the reactive power equation. Only if I know the value of P can I use the equation, or only if I know the value of Q can I use the equation. Because what am I trying to do? I will plug in the value that I know on the left hand side, right? That's a given, right? Then I will estimate the right hand side by plugging in values for V and delta. V I know at this bus, right? So V would be the right number. I will plug in here, it will be the correct V. because it's given at that bus, right? So all I have to do is put estimates for theta or delta, right? The angle. So I'll put an estimate for theta or delta here on the right-hand side, and then I will look at the difference, or I'll look at the equality. Are they equal, right? So then this is an equation I can use. But I cannot use the reactive power equation here because I don't know the reactive power. So I don't know, I'm not going to know the reactive power. It's also an equation in V and the angle, voltage and angle, right? So I don't know the voltage, and I also don't know the angle at this bus, right? And I don't know the reactive power. Right? So I cannot use that equation, and I don't know the left-hand side to be able to use the inequality. Right? I mean, only if you know the left-hand side can you use this not inequality. Can you use this equality to keep guessing values for the variables that you don't know at that bus? Okay, so I cannot use, so at a PV bus, I can only use one equation. Yes? No? Which equation can I use? The real power equation. I cannot use the reactive power equation at a PV bus, right? And then what else? So this is, we did 1, 2, 3, 4. I can use the P4 and Q4 equations, right? So now I have 1, 2, 3, 4, 5 equations and 5 unknowns, right? So now we will set up the power flow problem. Set up the power flow problem. Let's go back to the slides and then we'll go back to this. Is everybody okay first with which unknowns, which equations? Okay. So now, what these guys are telling us is like, let's set up this problem into a y equals f of x format, where y are the equations that you have, right? The p's and the q, p and q equations that you're able to use at that specific bus. Okay, so let's write up the y vector. Okay, the y vector, and they wrote it in a certain format. They sort of put if you go back here, they put the real powers first, and then they put the reactive powers first in sort of a sequence, and sequential order. So let's do the same thing, right? So how would I write my y vector? I would write what? P1, P3, P4, Q1, and then Q4. That would be my y vector, okay? And then my x vector, or vector of unknowns, they also do something similar. They write, if you go back here, they write all the angles first, and then all the voltages first, and then all the voltages below that, right? So I go back to my unknowns, and I write what? My angles first, so I have theta 1, and then theta 3, and then theta 4, and then V1 and V4. Okay, so now I have my x vector, my y vector, and then what else do I have? And my f of x, this p of x and q of x are the right-hand side. The equation, that summation. So this stands for the right-hand side, that summation. Remember, my left-hand side is equal to my summation, right? My left-hand side is equal to my summation. The left-hand side is all the p's and q's that you know at the specific buses, right? And the right-hand side is the summation, the summations that we have in terms of the voltages and angles, right? So this f of x looks exactly basically like y, right? Except that it's the unknown. It's the summations with these equations where you have v and delta unknowns that you have to plug in the variables and estimate, or guess the values of them and estimate. So basically, I need to construct my x and y vectors from the system. So I now constructed my x and y. What's the next step? Let's see. So blah blah blah. So remember, all V, P, and Q terms are in per unit. Everything, of course, is in per unit. The angles are in radians. The slack bus variables are omitted since I already know them, right? So that's all stuff we talked about. And we said that, yes, there are these, the P of x and the Q of x are the power flow equations, right, that we know at a specific bus. So the P of x and Q of x are these summations that we have, the power flow equations, at every bus. So these are my knowns. Pk is the power known at that specific bus. Qk is the power known at that reactive power known at that specific bus, is equal to that right hand side, right? So that's the equation. So what we will need to do is the following. If I have my, if I've now constructed this y equals f of x system, the first thing we do at the first iteration is plug in a guess. So plug in a guess for the v's and the deltas. I plug in a guess for the v's and the thetas or the v's and the deltas in on the right hand side, right? I plug in the guess and then I check the equality, or basically I do this y minus f of x and equals 0. I have something, some new variable, z of x is equal to 0. I've put it in this format. And this format is actually what we will numerically solve, right? The difference between them. So my real powers, or real and reactive powers that are known at the bus, minus the equation, the summation that I've plugged in my guesses into, they should equal 0. This should equal 0. If it's equal to 0, or of course it's never going to be equal to 0 because this is a numerical approach to solving the problem, it will never be equal to 0. So you have to agree, we will have to agree on a convergence criteria. So convergence criteria is something actually you control. Like in Power World, you control the convergence criteria to be maybe 10 to the minus 5, for example, right? It's never going to be 0. It's going to have to be smaller than a certain value. Unless you are, you can guess the perfect value. I mean, nobody can guess. I mean, you cannot. I mean, these things will not converge to 0. They will converge to something small. The difference will always be something small because the system is always changing, right? So you will agree on some convergence criteria. So we will plug in the guess, subtract the knowns, powers and active and reactive powers at the specific buses, minus the summations on the right hand side at every bus. If the difference is smaller than my convergence criteria, I stop. If the difference is not smaller than my convergence criteria, what do? I have to find another guess, right? So, and this is what the Newton-Raphson method, I cannot bring it back anyway. And this is what the Newton-Raphson method helps us do, basically. The Newton-Raphson method helps us solve or find this next guess for a system that we've sort of represented as in the terms of y equals f of x, or we've taken f of x and subtracted from y and equated that to 0. What it helps us do is find the iteration, the change in x's, or meaning x's are what? My x's are my v's and deltas, right? So they're helping us find the change in x, right, that I need to add to my current guess of x, right? X of I is my current guess of the value of x. X are the values of voltages and angles, right? And what Newton-Raphson method helps us do is find this delta that I need to add or subtract, of course, depending if it's a negative, subtract from or to the current guess, so that you can come up with a new guess, right? So that's basically what we're doing here, right? All we want to do is find a new guess, right? My new guess will be an increment from my current guess, right? So I want my objective is to find the delta x, which is the delta v and delta theta that I need to add or subtract to my current vector of deltas and v's. Okay, so how do you find that? Again, I will not prove the Newton-Raphson method for you, but basically it's one simple equation. That delta x is equal to the inverse of what is called the Jacobian matrix multiplied by your delta y's. Your delta y's are the subtraction of your known powers from the summations, right? So why was the PK and QK, correct? Delta y is the difference between the known pk and qk and the summation, right? So if I have at a specific bus, I know p1, and then I'm gonna write is equal to some summation, which is basically the, in terms of v's and thetas, right? It's the power in terms of v and theta from my power flow equation, right? This is what I started with, and then this is one element of my y vector, right? The delta y vector that they're talking about is basically the known value minus this summation. This is the sensitivity in power, right? This is the difference in power, right? If this is smaller than my convergence criteria, I will stop, correct? I don't need to calculate a new delta x anymore, right? But if it's not, so if delta y is greater than, your convergence criteria, which is, let's say, 10 to the minus 5, then you will have to find a new delta x. How do you find a new delta x? You find a new delta x using this equation. So you will multiply the Jacobian by your vector of sensitivities in power, right? Sensitivity, this is my delta y, the difference between the known power and the estimated power. Okay, you multiply that by the Jacobian matrix. How do you construct the Jacobian matrix? Right? The Jacobian matrix is a matrix of differentials that is differentiating each power or each element of your y matrix, your y vector. So my y vector is composed of these real powers and reactive powers, right? The differentials, the partial differentiation of, or the partial differentiation of my real powers, which are the f of x's that are available in the y vector. So these are my functions that I have. So my differentiations of real powers and reactive powers. So this is, let's say, dp1 by what? X's are what? The x's are my angles and voltages, right? So I'm differentiating my functions, the functions that I have in my y of x matrix, y of x vector with respect to the unknowns, right? So I'm looking at the sensitivity of real power at bus 1 to angle at bus 1. Real power at bus 1 with respect to angle at bus 2. Real power at bus 1 with respect to voltage at bus 3 or 4 or whatever, right? So I'm looking at the differentials of my y's of x's with respect to my variables. And I will construct a matrix based on that. I will see how we construct this matrix. I will go through an example here. Okay, so if I construct this matrix, the Jacobian matrix, and I'm able to invert it, and I multiply it by my vector of power sensitivities, then I can calculate my delta x. If I've calculated my delta x, that's it. I go back and each delta x I add to my current estimate to find my new estimate. And then do what? Take this new estimate and plug it on the right hand side of the power flow equation at that specific bus. And then calculate my delta y vector, which is the vector of power sensitivities again. If the subtraction is less than my convergence criteria, I stop. If the subtraction is not less than my convergence criteria, I have to find a new better guess. To find a new better guess, you have to construct the Jacobian matrix again. The Jacobian matrix changes every iteration, right? So I will not give you something like this with a 5 by 5 bus, a five bus system for you to calculate in the exam, right? Obviously, right? So if the maximum I can do is give you one iteration, give you one line of the vector, like what they do in the examples, right? I cannot give you. I can ask you on one exam. I said, okay, just construct the shape of the Jacobian matrix, and we will do something like that in class. Yes, ma'am.
Why does the Jacobian matrix change every time?
Why does the Jacobian matrix change every time? Because you are going to calculate a new delta. Good question.
Because isn't f of x supposed to be like fixed, يعني? Or does it change?
No, remember, no, f of x is not fixed.
They don't change every iteration, do they?
No, but you will have to plug in your values for v and delta every iteration.
The ones I got
Yeah.
from the previous.
Because it depends. Your p of x, which is your f of x elements, they contain v's and deltas, right? So you will plug in the value for v and delta every single time.
The new ones.
The new ones. So every single time you will plug in new values for v and delta that you've used in this iteration, right? So the values of it will change. The format, the equation for this differentiation will not change, right? And we will have the equations later. So the equation does not change, right? The equation for dp by d delta will not change. It's fixed. I agree with you because I just have a single equation there that I'm differentiating. But the elements of that equation, right? The elements of that equation contain the v and delta, right? So the value of that differential will change every time in the Jacobian matrix, right? Because every time you're plugging in a new v and a new angle. Does it make sense? Yes, sir. Yes, the Jacobian matrix is always invertible. The Jacobian matrix is always good question. And okay, so and what is the order of the Jacobian matrix? Yeah, in size. Remember, this is the differentiation of the functions that you have, which are the various variables in the p of x or f of x equation. So these are the number of p of x equations and q of x equations that you have, right? So remember, for a 5x5 system, we have possibly a maximum of 2 equations at every bus. That means that this matrix can maximum be a 10x10 matrix, right? But remember, for the slack bus, we don't have equations. We did not use the equations of the slack bus. We eliminated 2. So then it becomes an 8x8, right? Because I eliminated, becomes an 8x8 because I eliminated 2 equations from the 10x10. So at a PV bus, I can also use only one of the equations instead of 2. So then I can eliminate one more for that 4-bus system that we just did. For the 4-bus system that we just did, we had one PV bus, 2 PQ buses, and a slack bus. So for that specific system, let's just do it for that specific system. Is it? No, it's a 4-bus system. For that specific 4-bus system that we had one slack. This was a PV bus generator, and let me redraw the system again. Right, this was the system that we had. I called this bus 1, bus 2, bus 3, and bus 4. This was a PQ bus, PQ, PV, and slack, right? So here I have a 4x4 system. So maximum, so my Y bus matrix is what? What's the order of my Y bus? Y bus is a 4x4. Okay. How about the Jacobian matrix? No. It's going to be at least 8 by. I mean, it starts from an 8x8 because remember, at every bus I have 2 equations: the real power equation and the reactive power equation, right? So I start with an 8x8, and then I eliminate 2 for my slack bus because the slack bus I cannot use equations. I don't have equations. I don't have a P or Q at the bus, so I cannot use the real and reactive power equations. So now it's so instead of 8x8, it went down to 6x6. And then also I have one PV bus, which means I can only use one equation there. So now I have a 5x5 matrix.
So
right?
Can you repeat that idea again?
Yes. So the Y bus 4x4 number of nodes, right? The Jacobian matrix basically is based on you're constructing, you're differentiating each real and reactive power equation at every bus with respect to the unknowns, right? So it means it's equal to the number of equations that you have is tied to the number of equations that you can use at the various buses. At a PQ bus, I have two equations I can use. I can use the P equation, I can use the Q equation. At a slack bus, I don't have P or Q, so I cannot use any of the equations. I cannot use any of the power flow equations. At a PV bus, I can use one equation. At a PQ bus, another two equations. So 2, 4, 5. So it's a 5 by 5 Jacobian matrix. Yeah, for a 4-bus system, theoretically you can have an 8 by 8. No, 10. I was talking about the previous example that we had. Sorry, the 5 by the example that we did in class. Let's go to that and see, because I think that's what we do next. The 5 by 5 system that we had here. Here, this is a 5-bus matrix, a 5-bus system. This is a 5-bus system. There is one slack, right? One of these was slack. I think bus 1 was slack, right? Bus 2 was a PV bus, and then bus 5, 4, and 2. Bus 3 was a PV bus. 5, 4, and 2 were PQ buses, and 1 was slack, right? So 1 was slack, so I have no equations. 5 is a PQ bus, so I can use two equations. 4 is a PQ bus, so I can use two equations. 2 is a PQ bus, so I can use two equations. 3 is a PV bus, so I can use one equation. So the Jacobian for this system will be a 7 by 7 matrix. Okay? Because we build the Jacobian for this matrix in a later example. Yeah. That's why I was talking about 7. Okay. So here, for the system, for this 4-bus system that we had, here I have P1 at the first bus. I'm going to write the P's and I'm going to write the variables again, the y vector. I have the P1 equation I can use. I have the P3 equation I can use, and the P4 equation I can use, and then Q1 and Q4. And my x vector was theta 1, theta 3, theta 4, v1, v4. Right? So now my Jacobian is a 5 by 5. I will not fill it because it's going to be a big mess, but we can write a few of the elements here. Right, so this is my Jacobian matrix. The Jacobian matrix is, if you go back here, it's the differentiation of the first element of your power flow equation matrix, unknown power flow equations that you're going to be using with respect to your first variable. Same power flow equation with respect to the second variable, right? Same power flow equation with respect to the third variable. So it's my first variable, my first power flow. Remember, I started with real powers. So this is differentiation of P1 with respect to theta 1. Differentiation of P1 with respect to theta 2. Differentiation of etc. etc. Let's write this down. For our current system, let's say. So this is d P1 by d theta 1, d P1 by d theta 3, and d P1 by d theta 4, right? And then this is also dP1 by dV1 and dP1 by dV4, and then this is dP2 by d theta 1, dP2 by d theta 3, so on and so forth. Okay, so is everybody okay with filling up this matrix? Okay, so these are, so it's basically the power flow equations that we have, remember, it's a summation. right? It's a summation. And I think this summation is summing up the voltages at the various buses, right? So sometimes I'm differentiating with respect to that voltage at a specific bus. And sometimes that voltage at a specific bus will be a constant, right? Because if I'm not differentiating with respect to, if it's not a variable, it's going to be a constant, right? So anyway, we will not have to you will not have to go through the pain of differentiating this every time. The final form of the differentiation is there for you, and you will have it on your equation sheet. It's in your textbook, and you can just use it directly, right? So these are the differentials of power with respect to angles, power with respect to voltage. So real power with respect to angle and voltage, reactive power with respect to angle and voltage. This is everything you have, right? You're either differentiating real power or reactive power with respect to angles or voltages. So, and these are for the off diagonals of the Jacobian matrix. So for n does not equals k, right? So for the diagonals, these are the equations for the diagonals, right? They've differentiated them for you. You do not have to conduct a differentiation. And I think we write them again. So this is in here here everything is written in rectangular form. So the voltages and impedances are in rectangular form. So the YKN is the impedance magnitude, and theta Kn is the impedance angle, right? And Vk and Vn are the voltage magnitudes, and their angles are delta K and delta N, right? So we write them, so they wrote them for you in polar form. They also write them for you in rectangular form somewhere else. Let me see. Is it here? Yeah, this is in rectangular form. So the power flow equations in rectangular form, and I think the differentials in rectangular form are here as well. Okay, so everything is here, and they're in your textbook. So you do not have to memorize the equations, and you don't have to memorize the differentials. You do not have to conduct a differentiation, right? The differentiation is going to be fixed. You will have it in your equation sheet, and you will use it, and that's it, right? So let's go back to.
So what is the difference between an equal k and it doesn't equal k?
Diagonals versus off diagonals. So the
Like if
so
it's a
dp1 by d theta 1 is n equals k, right? The p2 by d theta 2 is n equals k, right? So these are the diagonal elements. But dp1 by d theta 2, so n does not equal k, right? So you have two buses, right? It's the differentiation of power at bus 1 versus angle at bus 1, right? This is, if I'm doing that, if this is an n equals k equation, then you have to use these bottom ones. If it's a off diagonal, you can use these top ones. Okay? We will substitute in one of these in an example now. But anyway, so do we understand the philosophy now? I mean, basically the whole thing is this calculation of this Jacobian and inverting it and multiplying it by the power sensitivities. Really, if you do that, then after you do this, you come up with your delta x. Your delta x, you take it, add it to your previous value of x, take that and plug it into the right-hand side of all your equations. Take your right-hand side, subtract them from your left-hand side, which are the p and q at the specific bus that you know. This is your delta y, the new delta y. If these delta y, the delta y vector elements are not all less than your convergence criteria, then you have to find a new delta x, and you keep repeating. Okay? So that's what Power World does. And you can actually, and I will show you a slide where, and Power World constructs the Jacobian matrix every iteration. So you can stop, you can actually make Power World step through. You know, do one iteration and stop. Do one iteration and stop. So you can use this as a way to check your answers. If you want to build a small system and, for example, do 2 iterations of that to confirm, you can actually make Power World do one iteration and stop, do one iteration and stop. And I think one slide I have here that shows how to do that. Okay, so another thing that can be in, so they sort of, you know, these are the differentials, right? But they also give them sort of some names here on the left-hand side, right? This J1, J2, J3, J4, and these sort of correspond to something I will explain next. So these are the different J1s. J1s are what? Differentiations of real power with respect to angles, right? And that, you know, remember the way we set this problem up is we've constructed the x as all the angles first, and then the voltages. Then we also constructed the y as all the real powers, and then all the reactive powers, right? Because of this construction, then the Jacobian matrix will end up looking like this. You will first differentiate real powers with respect to angles, real power with respect to angle, and then real power with respect to voltage. That's what we did here for the system that we had, right? Real power with respect to angle, real power with respect to angle, real power with respect to angle, then real power with respect to voltages, right? So here in this case, this is sort of where this is the J1 sort of that they refer to. And how far will it go? It will go down to here, right? This will be the J1. This will be the J2 that they are referring to, right? The real powers with respect to voltages. These will be the real reactive powers with respect to angles, reactive powers with respect to voltages. What is the significance? I will talk about that briefly now. This will be the J3. This will be the J4, right? Does everybody see? I mean, this is nothing special. They're just calling, okay, because of the way we constructed the vectors and the matrices, we ended up with a Jacobian matrix that has a defined sort of shape. And this shape sort of has all the real power differentiations with respect to angles here, all the real power differentiations with respect to voltages, real power differentiation with respect to angles. And then this is all reactive power differentiation with respect to angle, and then this is all reactive power differentiation with respect to voltage, just because of the way we construct, okay? What is the significance? It will help us simplify. Sometimes you just want to come up with a quick solution, and you have a 10,000 bus system, and you want to solve this quickly for some reason, okay? And when we will see that when we do this, we can simplify the matrix further, the solution very quickly, and I will show you how. Yeah. But let's first go to the slide as here. So everybody's okay with the structure of the Jacobian matrix and the order of the Jacobian matrix, right? Everybody's okay with those? And again, we just take in elements based on here, right? So you take these equations and you plug in, and we will do that in an example now. This is just the power flow equations in rectangular form instead of polar form like we had before. So these are power flow equations in polar form. You can use them in polar or rectangular form, and they're both in the text, right? Does not matter. Yeah. It depends on if you're given the impedances in rectangular or polar. So it's and here they sort of outline the procedure again. You start with, at a specific iteration, you start with a guess for angles and voltages. Then you solve your delta P or delta Q equations, which is basically subtraction of your known power and reactive powers from the right-hand side, right? And if this is not less than your convergence criteria, then you have to construct your Jacobian matrix. After you construct your Jacobian matrix, you can find your new delta V's, your new deltas, and new delta V, your new delta thetas and delta V's by taking this Jacobian and inverting it and pre-multiplying it by the power sensitivity matrix, which is what we just did. Okay. From there, you can find your new delta V's and delta angles and delta voltages. So you take your current angles and voltages, add them to your delta or your change in angles and voltages, and you construct your new guess for angles and voltages and keep repeating. It's smaller than whatever you decide is your convergence criteria. You decide the convergence criteria. So, okay. Let's do an example. I think that would be good. So determine the dimension of the Jacobian matrix for the power system in example 6.9, and we did that. Also calculate delta P2. So they're looking for what? The power sensitivity at bus 2 at iteration 0, right? Delta P2 is the power sensitivity at the real power sensitivity at bus 2 at iteration 0, right? So this is P2 minus the right-hand side, right? This is P2 minus the right-hand side at iteration 0. So I'm going to use my initial guess for voltages and angles, plug them into the right-hand side, and go to bus 2 and see what the real power is, subtract them from each other. That's what they're asking for here, delta P2, right? And in step 1, and find the Jacobian matrix element J124. J124, we go back to our setup here. So this is n does not equal k. So go to our equations that we have here. Where are the equations here? J1, 2, 4, right? So they're looking for the differentiation of real power at bus 2 with respect to angle at bus 4, right? J1, 2, 4, right? So they're looking for element J1, 2, 4, which is the real power at bus 2 with respect to angle at bus 4, right? That's what they're looking for. Okay, so they're looking for that in step 2 of the Newton-Raphson iteration. Also, but they're looking for that at also iteration 0, right? So this is it's step 2 of the Newton-Raphson method that we just described, but basically they're looking for that at iteration 0 as well, right? And then assume 0 initial phase angle and 1 per unit voltage magnitudes, except V3 is equal to 1.05, right? So so that their initial guess for all voltages except V3 is 1. V3 would be 1.05, and all angles assume equal to 0 in the first iteration. The other thing that I did not mention is the following. Like the Y-bus matrix, if you go to our example here, let's also write the Y-bus matrix for this system. We said the Y-bus here would be a 4x4 matrix, right? So this is what? Let's see, this is Y. It's Y11, Y22, Y33, Y44, and this is Y12, right? Y13, Y14, and these are, it's symmetric, right? So this is going to be Y21, right? And this is Y31, Y41, right? It's a symmetric matrix. So what is Y? This is Y2. This is Y2. Does everybody agree this is element Y23? Right? So what is element Y23? What? It's negative of the impedance between buses 2 and 3. Buses 2 and 3 are not directly connected. So it's 0. So it's negative of the admittance, not impedance, right? So since they're not connected, then the admittance between them is 0. There's no admittance between them, right? So Y23 is 0. Do we agree?
So aren't they connected on the right? Yeah.
What?
Aren't they connected?
Not directly. It's only the admittance directly between bus 2 and 3. This is 2. Where's 2? Where's 2? Sorry. Sorry, not 2 and 3. Sorry, this is. So I meant bus 1 and 3. Sorry. So this is 1, 3. Sorry, I was looking at the wrong numbers. 1, 2, 3, 4. So admittance 1, 3, Y 1, 3 in the admittance matrix is 0. And is anything else 0? So bus 1 is connected to bus 2. Bus 1 is connected to it's not connected to bus 3, so the admittance is 0. Bus 1 is connected to bus 4, so that exists as well. So this is fine. How about from bus 2? Bus 2 to 1 is fine. 2 to 3 is fine. 2 to 4 is connected as well. So how about 3? 3 to 2 exists. 3 to 1 does not exist. Y13 is equal y31 because the matrix is symmetric. So y31 does not exist, it's 0. y34 exists here, there's a transmission line here between them, so it exists as well, right? So in this matrix I have, in this y bus matrix, I have two zeros at y13 and y31, correct? The Jacobian matrix is the same, right? The sensitivity of real power at bus 1 is not affected by angle or voltage at bus 3. It is affected by angle or voltage at the buses that it's connected to, right? So there are also zeros in the Jacobian matrix that I didn't mention. Okay, so the admittance matrix has zeros because of the direct connectivity. And the Jacobian matrix also has zeros because of the direct connectivity. So if I'm looking at here, for this system, dp1, this is 1 now, okay? This is dp1 with respect to d theta 3, which is this. This is 0.
What about
Right? What else?
dp3 with respect to d theta 1?
This is 3, right? dp3. Also, of course, it's also symmetric. So this is dp1 with respect to d theta 3. That's equal to 0. And this is similarly 0. dp3 with respect to d theta 1. Power here with respect to the angles at this bus. It's not connected to it, right? So you change these angles, it will not really directly affect it. What will directly affect it is the buses that it's connected to, okay? So let's construct let's put all the zeros. Let me erase this, and let's put in the y bus and the Jacobian fill it up with zeros. Wherever we have zeros, let's fill it up. So at least I feel comfortable that I at least covered this topic properly. Yeah. 1, 2, 3, because it's important for something else later. So this J1, it's related to this J1, J2, J3, J4. There's something else related to it. Yeah. This is my Slack PV. Okay. 1, 2, 3, 4. Okay. So let's Y bus. Okay. So this is y11 here, and then y12, and this is 0. Where else do I have a 0? Remember, this is a symmetric matrix. So this is y31, and this is y13, y13, and so is y31. This is also a 0. Okay. Everything else has values in the admittance matrix. So everything else will have values based on the data that you have for your cables and transformers or whatever you have. Okay, so this is the Y bus matrix. The Jacobi matrix. Let me actually. It will be easier if I also write the Y. Delta P1, delta P3, delta P4, delta Q1, and delta Q4 is equal to this. I'm writing this equation down, right? I'm writing my power sensitivities are equal to my Jacobi matrix multiplied by my angles, right? For this example here. Okay. My angles are what? Delta what? These are all deltas, right? In my sensitivities and angles, right? So it's theta 1, theta 3, theta 4, and then V1 and V4, right? And then I can make a big mess here. Right? And these are, this is now my J1, right? This here, this zone is the J1, this is the J2, J3, and J4. Okay? Where are my zeros?
And dp1 by d.
Yeah, so the dp1 with respect to d theta 3 and the j1, yes, so it will be dp1. This is all the dp1s by the d thetas, d theta 1, d theta 2, d theta 3, right? So dp1 by d theta 3, which is the second element here, it should be 0. This is dp1 by d theta 3. That's 0. Where else do I have a 0?
dp3 by d theta 1.
Sure. So same thing here, dp3 by d theta 1. So it's the first element here, right? Where else do I have a 0?
That's it.
No. But it's the same for reactive power and voltages. Same.
Okay, so dq1
So dq1
by d theta 3.
dq1 by d theta 3. So which element?
The second element.
Second element. Correct.
And
This
the
is also
first
0.
element,
Where else do I have a 0?
dq4 by d. No.
Huh?
that's-
No, there's one more.
that's it.
No, there's one more. There's one more. Remember, the differentiation of power, whether real power or reactive power, with respect to any angles or voltages here, will be 0. So here I also have, remember, this point is what? dp1 by d theta 1, dp1 by d theta 3, dp1 by d theta 4, dp1 by dv1, dp1 by dv4.
There is a connection.
So here, there's nothing here. There's no more zeros here. So this has value, this has value, this has value, this has value. This is 0. This has value, this has value. We're okay. How about this one? dp3
By dv1.
dp3 by dv1.
0.
That's 0. Everything else is okay. Will have values. Is everybody okay with the zeros? Okay. So this is the structure of the Jacobi. So from the structure of the Jacobi matrix, you can actually, if I give you the admittance matrix, you can actually go back and construct this small system, correct? Because you know that, okay, you will look at the zeros. The zeros is between 1 and 3. So you know that bus 1 and 3 are not connected. And you know you have 4 buses because of the order of the system. So if I give you this and I tell you construct the system, the corresponding system, right? You can, okay, you 4 by 4 white bus. So 4 buses, how do you connect them? Everything is connected except buses 1 and 3. So you put cables between everything except buses 1 and 3, correct? You can easily build this system from this admittance. You can also do the same from the Jacobian matrix, right? If I give you the Jacobian matrix and tell you to construct a system, here the additional thing is you can also identify what the buses are, right? Because if you're given this, if I'm giving you this, you know that, you know which variables exist, you know which variables you have, which variables you don't, so what knowns and what unknowns you have at the specific bus, right? So you can actually go back and construct this system from knowledge of this equation, and then you can tell me also which buses, what buses are what in every at every bus, what information you have at every bus, and what is unknown. Everybody's okay with this? Okay. So I will keep this because I will use it again for something else now. So this example forced me to do this because of the following, right? So now they want us to calculate the power sensitivity at bus 2 for iteration 0 and the differentiation of real power with respect to angle at between buses 2 and 4, right? So I will go to my equation for I will go to my real power flow equation. So this is my delta P2, sensitivity of my real power at bus 2. So I have to go back to the system, right, and see what's on my left hand side. So back to my system. Sorry, where's the system? This is my system here, right? This was my system. At bus 2, I have a load, right? Its real power is 800 megawatts and its reactive power is 280 megavars. The base power was 100 megavars. So if you go look at the base power here, base power was at 100 MVA, right? So you go to bus 2, the bus 2 had a load of 8. Remember, the power at every bus, PK is equal to generation power minus load power. So which means that P of 2 on the left hand side is equal to what? You remember my left hand, okay, what I mean by left hand side and right hand side is, the left hand side is the known power at a specific bus. Left hand side is the known power at a specific bus, whether active or reactive. And the right hand side is the summation, right? So here, all of these buses, I know the left hand side, right? I know that at bus 1, I have my real power. I know at bus 3, I have real power. I know at bus 4, I have real power. And I'm trying to calculate the difference in real difference. This is delta. This is the difference between the left-hand side, or your real power, or the power at a specific bus, minus your summation, right? So now I have to go back. For me to fill these up, now I have to go back and look at every specific bus. They're asking us for P2 iteration 0, or delta P2 at iteration 0. Delta P2. Delta P2 means P2 minus the summation, right? So I have to know what P2 is, right? So I go to my bus, my system, and I look at what I was given. I was given that this bus 2 is a load bus with a real power at the bus equal to 8 per unit and a reactive power at the bus equal to 2.8 per unit. So remember when we were looking at the specific powers at a specific bus, we were saying I would go to every bus and look at the specific power. The specific power at the bus, or specified power at the bus, is the difference between what is the generation power and the load power at the specific bus. Here I don't have a generator. At bus 2, there's no generation, so it's 0 minus the load power, right? And load power is 8 per unit, so it's 0 minus 8, so it's minus 8. So the left-hand side is going to be minus 8. That's why you will have a minus 8. Sorry, here. This is a minus 8, right? This is a minus 8 because P2 is the specified power at bus 2. It's generation power minus load power. Generation was 0, load was 8, so it's minus 8. Minus your right-hand side, minus the summation, right? Minus the summation of the right-hand side. This summation is the P2 summation. So you go back and look at your equation for the summation that you have at specific. So you look at the real power flow equation, substitute with the K equal to 2. And let's look at that. Where is the real power flow equation? Let's look at it in here. So this is my power flow equation. So P2 is going to equal V2 summation of Y2, then N. N starts with 1. So Y2, 1, V1, right? Then cosine, blah, blah, blah. And then Y2, 2, V2, blah, blah, blah. So on and so forth, right? Sometimes these Y's will be zeros, right? So in our example here, which ones are zeros?
Y31 and Y13.
No, but sorry, the example that they have in the textbook, the 5-bus matrix, 5-bus example. So here, which admittances are 0? So 1 and 2 are 0 because they're not directly connected. And 1 and 3. Anything else?
So how about
3 and 1 also. Yeah, 1 and 3 is 3 and 1, right? So 1 and 3 are not directly connected.
what about 1 and 4?
So somebody take note of those. So 1 and 4, 1 and 4 is also not directly connected, right? But we're looking at bus 2 now. Right? They're asking us to calculate P2, right? So it's going to always be Y2 something, right? If you look at the power flow equation, right? Where's the power flow equation that I have? Power flow equation is here, right? So it's going to be the real power flow. So it's going to be Y2 something. So let's look at everything not connected to bus 2 because that will have a corresponding admittance of 0 in the power flow equation, right? So let's look at our example. If we look at our example, bus 2 is connected to 5, 2 is connected to 4. So Y21 and Y23 are zeros, right? So the summation will originally have 5 terms, right? Because the summation will include all the admittances, right? Where is the summation? The summation is here. The summation is from Y equals 1 to N. N is the number of buses, right? So originally I have 5 buses. So originally I have 5 buses here. So the summation for real power would be Y21, Y22, Y23, Y24, and Y25. Multiplied by the cosine, 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 all these angles, right? I will find that Y21 and Y12 are equal to 0. Y23 and Y32 are equal to 0. So out of these 5 terms, I will only be left with 3, right? So let's go back and make sure that this is the case. Here. Okay, so they write all the 5 terms down. So Y21 V1 cosine the angle of V2 and minus the angle of V1. Remember, they told us all the angles will be 0 and all the voltages will be 1 except V3, right? It will be 1.05. So V1 will be 1 and the angles will all be 0. And this is the angle at iteration 0, right? This is the angle of V2 minus angle of V1 at iteration 0. They didn't substitute the value. The substitution is here. They're just, this is the summation. They're expanding the summation for you here. And it's 1 term, 2 terms, 3 terms, 4 terms, and 5 terms. Y21, Y22, Y23, Y24, and Y25. So this is the summation that expanded. And then we have to substitute with the values for the admittances and the voltages and angles. Admittances, we know that Y24, right? Which Y's were 0? Yeah.
2, 1, and 2. Yeah.
2 of them were zeros, right? 2 of them were zeros. So that's why here you will find that this is 1 term here, 2nd term, 3rd term. You will find that this is only 3 terms. Minus 8 is the power, the specified power. Minus 1 is the voltage at bus 2 for iteration 0. Open quotes, and then they have only 3 terms, right? 3 terms because 2 of the admittances were 0. And then, they found the answer, V2. Okay? I'm not going to substitute, you substitute, okay?
So,
Yeah. What?
I just wanted to ask about the angles. Which angles are we supposed to guess as 0?
Yeah,
The
so they told you.
thetas or the deltas?
No, remember the deltas here is the angle, delta 2 is the angle of voltage at V2. The delta 1 is the angle of voltage at bus 1. So sometimes the equation is written as theta 1, 2 or delta 1 minus delta 2. Theta 1, 2 is the angle difference between bus 1 and bus 2, right? But remember, since everything is going to be with respect to a slack bus, which is 0, so we can actually just use the specific angles at that bus. But for now, I mean, just the textbook, if you want to use the textbook equations, they will give you voltage at a specific angle, voltage at a voltage with a specific magnitude and an angle. So you just use the deltas. I mean, whether you use deltas or thetas, it's in the equation, it's the same. So, yeah, they gave you, sorry, so they told you that the angles,
Initially, they're zero.
yeah, and this equation is basically the power flow equation that the textbook uses, which is, this is an equation that, this is like delta I minus delta K, right? This is not what the textbook uses. The textbook expands this as delta I minus delta K. So delta I will be the angle of VI, delta K will be the angle of VK. So so sometimes you may see it in textbooks theta I K, which is basically delta I minus delta K. But I would just use the textbook equations. Use the textbook equation, and you will be given voltage and angle for every single bus. Yeah. Okay.
So thetas are always the difference between the deltas.
Yeah, the theta is the difference between the two deltas. Yeah. Basically, the angle between the two, the angle difference between two buses. Yeah. And then the next thing they want in the example is, I know we finished, but the next thing they want in the example is they want element J1, 2, 4 in the Jacobian matrix at iteration 0, right? So you go to, same thing, you go to your J1 equations. N does not equal K because they want 2, 4, right? So they go J1, 2, 4. So dP2 by d delta 4, right? So you're going to use this equation, right? So this equation means you're going to have Vk, so this is going to be V2, Y 2, 4, V4, sine delta 4 minus delta 2 minus the angle of the admittance between bus 2 and 4, right? So it's a single element that you have to calculate. They do the calculation for you here. So it's V2, Y24, V4, sine delta 2 minus delta 4 minus theta 24. Okay? So now you can construct your Jacobian matrix. Basically, if you go through, you can build the whole Jacobian matrix. You can also construct your power sensitivity matrix and look at if your convergence criteria is satisfied or not. Yeah. So we'll stop here. So basically, I mean, I cannot solve a full 5x5 system or whatever. I think in the class, I think in the recitation, maybe Adil will solve maybe a small 2x2 system for you to go through. I'll ask him to solve a 2x2 system with 2 iterations. So you start with 0, and you find one Jacobian one time and do it, and then that's it. I mean, so that you can go through the full system. But this is basically what we just did here, but on a specific element. Yeah. So any questions?
So,
Yes.
what's the most you give us to do on an exam by hand, I guess, or in homework?
It's like
One by one.
find an element. Maybe give